In this example of constrained optimization, we're still going to be using pen and paper techniques. So we're going to be using Lagrange multipliers, and we're going to apply this approach to an example coming from math biology involving alleles, which are alternate versions of genes. Now, the long and the short of it, there's 3 different alleles that are responsible for 4 different types of blood. And there's a law called the Hardy-Weinberg Law that suggests the proportion of individuals in a population who carry 2 alleles. So what we care about in this case is that this proportion, capital P, is equal to the following sum of terms: 2 times little pq plus 2 times little pr plus 2 times little qr, where little p, little q, and little r are the proportions of the 3 different alleles, respectively, in the population. Now, the constraint on this problem that we have is, well, since we're dealing with proportions of populations, little p plus little q plus little r, this whole thing should equal 1. So that is our constraint in this problem. And now in class, we've been doing a lot of examples involving equations of 2 variables with 1 constraint. So this, as it stands, this looks like there's 3 variables and 1 constraint. So I'm just going to make this assumption that the population we're looking at, we know something peculiar about maybe allele R in this case. And we're just going to make the assumption that R is equal to, well, let's just say little p over 2. And full disclosure, the only reason we're doing that here in this case is just so we can practice again a constrained example where we have 2 variables, 1 equation, and 1 constraint. So if we do that, basically we can just use this information to reduce our problem into a problem involving 2 variables and 1 constraint. So let's see how this works out. Well, this is a constrained optimization problem using Lagrange multipliers. So we have our Lagrange function. The Lagrange function is a function of the variables p, q, and r. We'll get rid of the r shortly. And that's going to be equal to capital P, the proportion function, which is a function, again, of little p, little q, and little r. And then we subtract off our Lagrange multiplier times the constraint. Now, in this problem, we know that the constraint is p plus q plus r equals 1. But remember, in Lagrange multiplier problems, we like that constraint basically equaling 0. So we're just going to rewrite this constraint as p plus q plus r minus 1 equals 0. So then we take that p plus q plus r minus 1 and just multiply it by that Lagrange multiplier sigma. All right, so I'm just going to substitute what we know so far. We'll do some arithmetic cleanup in a moment. So capital P is equal to the sum of p times q plus p times r plus 2qr. And we subtract off sigma, our Lagrange multiplier, times that constraint, p plus q plus r minus 1. Now, everywhere there's an r in the equation, we're basically going to just substitute that with p over 2. Remember, this was an assumption basically just to turn this problem involving 3 variables into the constrained optimization problems we've done previously. So anywhere there's an r, we just substitute p over 2. So our Lagrange function now becomes just a function of the variables p and q. So again, just substituting p over 2 anywhere there's an r. And we'll simplify this momentarily. All right, so our Lagrange function again is now just in terms of 2 variables, p and q, and our Lagrange multiplier sigma. All right, so just simplifying this a little bit more, we basically get that Lagrange function is p times q plus 2p squared over 2, or in other words, plus p squared, plus 2qp over 2, or in other words, plus pq, and then minus our constraint, which it looks like we can reduce this to just 3/2 p plus q minus 1. Okay. Oh, I guess there's a little more simplification we can do. We can combine the 2pq and pq. So our Lagrange function looks like it finally is equal to just 3pq plus p squared minus that constraint. All right, so that is our Lagrange function that we're going to approach using basically the optimization methods that we know from multivariable calculus. The first thing we do, just to give us the roadmap, we take the gradient of that Lagrange function, we set that gradient equal to 0, and that gives us our candidate solutions for these points of interest. And then from there, if we want to show it's a max or a min, we take the Hessian matrix. And because this is a constrained optimization with Lagrange multipliers, we have specific conditions on the determinant of that Hessian matrix that will tell us if it's indeed a max or a min. So the first thing we need to do is, well, we need to compute the gradient of L and set it equal to 0. And again, this gives us our candidate solutions. So if we just take the partials of L with respect to each variable, including our Lagrange multiplier, the gradient is a vector. So partial L, partial P, partial L, partial Q, and finally partial L, partial sigma. So that's right, we even take the partial derivative with respect to our Lagrange multiplier. We set each of those individual entries of that gradient equal to 0. And when we find that solution, as again, we're looking for values of P, Q, and sigma that satisfy those three equations there, we have our candidate solution. Another way to look at this is we're basically building a system of 3 equations for our 3 unknowns, P, Q, and sigma. All right, so let's take all those partial derivatives individually, set them equal to 0, just to see what we're working with. All right, so first, partial L, partial P. We find that the partial derivative of our Lagrange function with respect to P is equal to 3Q plus 2P minus our Lagrange multiplier times, well, 3/2. And we're setting that equal to 0. I'm going to go ahead and just call that equation 1. And again, the reason for doing this is just so we can keep track of equations, so we know what we're substituting into what equation, and so on and so forth. Next, we take the partial derivative with respect to Q. And taking the partial derivative of Lagrange function with respect to Q, we will just get 3P and minus, actually just minus sigma. And again, we want to set that equal to 0 because that's what we do with each of those partials inside of our gradient. All right, I'm going to go ahead and call that equation 2. All right, finally, taking partial of our Lagrange function with respect to sigma, we basically just get back what that constraint is. But we have minus times the constraint, 3/2 P plus Q minus 1. And again, we're setting that equal to 0 because each of those partial derivatives we set equal to 0 because each of those are the terms in the gradient. All right, so we now have this system again. If we look at this, this is a system of 3 equations and 3 unknowns. Our unknowns being P, Q, and sigma, our Lagrange multiplier. So we should be able to solve this system. Now, the way in which we have done this previously in class, if this was a linear system, we set up a linear system just like in linear algebra. So we use all of those types of matrix methods that we had at our disposal. I'm just going to go ahead and do the substitution method because that's typically what we do for nonlinear functions. Although if we look at the equations that we have, all the equations we have are actually linear. We only have P, Qs, and sigmas to the first power. We don't have any P times Qs, Qs times sigmas, P times sigmas, or anything like that either. So this is actually a linear system that we could approach using matrix methods. I'm going ahead and just practice substitution for us. And the first thing I'm going to do is just look at these equations and ask myself, which equations does it look like is easy for me to solve for one of those variables in terms of the other? And hopefully you see that, well, equation 2 looks like I can pretty easily solve for just P in terms of sigma, or sigma in terms of P. So let's just go ahead and start with that. So the first thing we'll do is solve equation 2 for sigma. All right, so equation 2, we have 3P minus sigma equals 0. And then we finally just get that sigma equals 3 times P. Okay, that's maybe not too exciting, but again, I want to emphasize what we're trying to do is basically set up a method to go forward to figure out what each variable is in terms of other variables, and then sequentially knocking down the amount of unknown information we have. So now that I know sigma, I'm going to go ahead and just plug that into equation 1, where I have that sigma from equation 1. So the second thing here is I'm going to sub what we just found that I called equation 4 into equation 1. So in other words, we're just going to substitute what we just found for sigma into sigma from equation 1. So we have 3q plus 2p minus 3 halves sigma equaling 0. And again, we know what sigma is in terms of p, so we can substitute that in directly. So we have 3q plus 2p minus 3 halves times 3p equaling 0. And now if we look at this, we notice that this is actually an equation that has 2 variables in it now rather than 3. We just have p's and q's. So I'm just going to do a little simplification here to make this a bit nicer. So we have 3q plus 2p minus 9 halves p equaling 0. And I'm just going to find common denominator between those last 2 terms so we can put those p terms together. Common denominator being 2. So what this equation turns into is we have 3q minus 5 halves times p equaling 0. And well, what we can see now is we can directly get a relationship between the variables p and q, similar to how we have already a relationship between sigma and p. So I'm just going to go ahead and solve for q in terms of p. So we get 3q's equal to 5 halves p, and then we find that q is equal to, well, 5 over 6 times p. So now because we have a relationship between q and p, we also have a relationship between q and sigma. I'm going to call this equation 5. So what other information do we have that we haven't used yet? Well, going back to our original equations, we first used equation 2, we then used equation 1. What we haven't used yet is equation 3. So I'm just going to pull down equation 3 down below and see what we can use it for. So I'll just say recall equation 3. So equation 3 itself is basically just in terms of p and q. So we could have found a relationship between p and q from this equation, although we already found a relationship between p and q. So what we can do is actually just, well, anywhere there's a q, we can substitute in what we know for q already from equation 5. So I'll just say substitute 5 into equation 3. So if we go ahead and do this, I have minus the quantity 3 halves p plus, well, 5 6 times p, and then minus 1 equaling 0. And now if we look at this, we see an equation only in terms of p, so we can solve for the value of p. So we only have one equation, one unknown at this point. So let's go ahead and do that. The first things first, we can get rid of that minus sign, just divide both sides by -1. And then we can start combining some of this p information. So we have 3/2 p plus 5/6 p. We'll find common denominators in a moment. And kicking that 1 to the right-hand side, we have equaling 1. So let's find common denominators. It looks like a common denominator of 6 will work. So multiplying the first equation by 3/3, we get 9/6 times p plus 5/6 times p equaling 1. So we find 14/6 times p equals 1. So in other words, we know what p is equal to. P is equal to 6/14 or 3/7. So we found our candidate value of p, which we'll call p star. Now, what's useful about that is, well, since now we know p, going back to equation 5, we now know what q is. So q is equal to 5/6 times p, which we now know is 5/6 times, that's right, you guessed it, 3/7. So q star is equal to 15/42. And finally, the last thing we need is the value of our Lagrange multiplier sigma, which if we scroll back even further from equation 4, we know that sigma is actually just equal to 3 times p. So I'll call it sigma star. That's equal to 3 times p, which we found to be 3/7. So there is our candidate solution for this constrained optimization problem. Now at this junction, we haven't proven if this is actually a maximizer of capital P. Again, if we go back to the beginning, what we're interested in is maximizing that value of capital P. How do we do that? Well, we will take the Hessian matrix of this system, which is actually what we call a bordered Hessian because it's a Lagrange multiplier problem. And we consider its determinant, and the determinant will tell us whether or not it's a max or a min. So remember, we had a theorem from class that helped us tell in this types of situation, which we have one equation of 2 variables and one constraint, whether that determinant of the bordered Hessian tells us if it's a max or a min. So to use this theorem, we clearly need to figure out what the Hessian matrix is. So this brings us to part 2. Compute the bordered Hessian and find its determinant. All right, so let's just go from where we had. So remember, we had our gradient of Lagrange function, partial L, partial P, partial L, partial Q, and partial L, partial sigma. When we take the Hessian matrix, we're looking for a matrix of all second order partial derivatives. Our Hessian will be a function in general of our variables of the system, including that Lagrange multiplier. And when we take the Hessian matrix, we consider each row to be basically different partial derivatives of each entry of that gradient vector to begin with. So basically the way the first row works is we'll take the partial derivative of P on the first entry of our gradient. Then we take the partial derivative of Q on that first entry of our gradient. And then we take the partial derivative with respect to sigma of that first entry of our gradient. And each row will work exactly the same, except what we're taking, the actual thing we're taking the derivative of changes as we go row to row. So let's write these out really quickly. And while I'm writing this, some of the properties of this matrix is that it is still going to be symmetric. So that's a bad signal. Okay. So we have quite a few partial derivatives we get to take here. But again, this is the way that we structure these Hessian matrices. All right, so I'm just going to go ahead and grab basically what we had from before of those partial derivatives. I'm not going to include setting them equal to 0 though, because again, we're just taking the derivative of those entries of the gradient itself. So those are our entries of the gradient that we found from before. So let's start computing this Hessian matrix. So again, we focus first on this top row, taking the partial derivative of that top row there, partial L partial P with respect to P, we will just get a 2. Taking the partial derivative of that with respect to Q will just give us a 3. Taking the partial derivative of that with respect to sigma will give us a -3/2. All right, let's go down to the next row. Looking at the next row now, we'll take all those partial derivatives. Partial derivative with respect to P will give us a 3. Partial derivative with respect to Q gives us a 0. And partial derivative with respect to sigma gives us a -1. Now going to that last entry of our gradient, taking a partial derivative with respect to P gives us a -3/2. Taking the partial derivative with respect to Q gives us a -1, and taking the partial derivative with respect to sigma, that gives us a 0. So there is our Hessian matrix in this case. It is symmetric, so we did everything correctly. It should still come out symmetric. And now what we're interested in is finding the determinant of this Hessian. So again, if we take a look at our theorem, what we actually want to show that this is a local maximum is, well, we want the negative of this determinant to be negative. So we're hoping to see here is that when we just take the determinant of H, it comes out positive. So we multiply by a -1, we get this negative condition. All right, so let's start taking this determinant. And well, let's take the determinant across this bottom row, basically because we see that big old 0 kind of sitting there. Or you could do this determinant across that last column as well. All right, so the determinant of H, first we have that -3/2 times that submatrix. So we'll take -3/2 times that determinant. Next, we have a minus coming from the every other plus minus scheme for taking determinants times that -1, which is just that term that's there in the second entry of the last row, times the determinant of the matrix that's left over, the matrix including basically those two terms and those two terms. All right, so let's go ahead and compute this determinant. So we have equals -3/2, all times now 3 times -1 minus a -3/2 times 0. And then we have a minus, we get a +1 times the determinant of its 2 by 2, which is 2 times a -1 minus a -3/2 all times 3. So So let's see what happens. We have that this is equal to, well, minus 3/2 times a minus 3 times a, well, 0. So what's more important for us to notice is this term, that thing's positive. That's really just what we care about when doing these determinant calculations. Are they positive? Are they negative? And so on. And then we're adding to it. Well, what do we have here? We have a minus 2, and we have a plus 9/2. All right, so what about this? This seems like it's something positive as well. So we have positive plus positive. We can argue that, well, the determinant overall has to be positive. Let's actually just go through this arithmetic though. All right. So just going through this last arithmetic, we have 9/2 minus 2 plus 9/2. So we have 18/2. If we find common denominators, we have minus 4/2, which is equal to 14/2, or this determinant is equal to 7. So the determinant of our bordered Hessian is just equal to 7 itself. So what that implies then is, well, the negative of the determinant, so again, I'm stressing to use this theorem, negative of the determinant of our Hessian is equal to, well, now minus 7, which is a negative number. And by this theorem, since the determinant is the negative of our determinant is negative, we know that this is a maximum. Those are the general steps for doing a Lagrange multiplier problem in which we have 2 variables, 1 equation, 1 constraint, and we go through actually showing that something is a max or a min.